Hi, everyone, and welcome to today's session. Today is a very impactful and meaningful session to me because this consolidates the learnings of my 5 years of PhDs all into one session. So when I first started out my PhD, it was during the time of AlphaGo and AlphaZero. Lee Sedol just lost to AlphaGo, and I was thinking that, wow, humanity is at an age where we are going to reach super intelligence. And then I joined wanting to contribute. So my first few experiments were on AlphaGo. And then I realized that this algorithm is not going to take us to super intelligence because it is too fixed, too constrained to that particular environment. So I want to create an agent, or rather a group of agents that can learn fast, adapt well to one another, to the environment, and can be made to do like arbitrary tasks, like, a swarm of drones doing a light show maybe, or like a swarm of repair bots building a house. Yeah, so that'll be eventually the end goal. So there's a lot of things that are still missing from current kind of technology. And this is actually more or less like a starter of the whole journey. After this whole PhD thesis thing, I still intend to spend 5 to 10 more years researching more and improving the system. So without further ado, let's begin. So what's the main thing about AI systems, right? Humans, like you and I, we actually can learn pretty fast. Like I have two kids, and if I just show them some flashcards of like giraffe pictures, soon enough, if I bring my kid to the zoo, he will be able to tell me, hey, that's a giraffe. Okay, you try to do that for AI systems. You just show them cartoon pictures of giraffes and ask them to generalize to real world giraffes. I think that's very unlikely. Even like convolutional neural networks, you will still need to give those examples like real world pixels versus, stuff like cartoons are quite different. So in order for AI systems to generalize, it might be difficult. So traditional AI systems, especially in the deep learning era, requires lots of examples to learn. Okay, one might tell me that LLMs don't need much examples. You can few shot learn everything. Okay, but think about it. Even a large language model requires a lot of training data. In fact, the entire web's worth of training data in order to do this kind of in-context learning. So yes, they do need quite a lot of examples to learn, and they do not really adapt very well to changing environments. Okay, case in point. Okay, last time I will talk about deep neural networks, like, you train on like MNIST digits 0 to 9, and then you add in a new digit, new letter A, B, C. It can't really classify those because it's not trained to do that. All right, now you can take a look at large language models. Large language models, they might be able to code out some code. Okay, let's say if you are coding for like maybe Python. Python is the coding language, Python version 3.9 maybe. Let's say if there's a Python version 4, all right? If you don't train it on Python version 4 in your pre-training, you ask it to code it, that Python that might be different in syntax, it tends to lead to a lot of errors, okay, because they do not adapt to the new environment well, all right, the new coding language. That's why stuff like Devin, is great to do software coding, but if your packages get updated, then they can't really recommend the right things, right? So this lack of adaptiveness is a huge problem right now, actually, because if we want AI agents, we kind of need them to adapt, right? So this is a very pertinent question. How do we get AI agents or AI systems to be like humans, to learn quickly, adapt quickly, right? How can we use insights from our human brain to build better AI models? And note here, I am not talking about replicating the brain exactly neuron by neuron, neurotransmitter by neurotransmitter. We don't have to do that. What we need to do is to see how the structure or how some of the psychological insights that the human use, like for example, hippocampal replay and so on, and how can we use it to imbue into our algorithms to make them better and more efficient. Right, so I hope this is the good starting point for all this. So this is the overview of what I'm going to touch through in this presentation. I'll be emphasizing more on this learning fast and slow because this is an idea that I took about 4 years to come up with. All right, so this whole cycle is a journey of me trying to discover my thoughts. All right, so I started off with DropNet. DropNet is an iterative pruning model where we just prune away the nodes that have the least average activation value, okay, which are actually the least important nodes. After you prune away those nodes, you still have the final architecture. And I realized that this final architecture, even after you reinitialize your weights to the original weights, you can still learn with this. So this means that we have found an ideal structure. So DropNet is a way of consolidating knowledge by pruning away unneeded connections. Okay, actually in the brain, we also do this kind of dropping of weights, dropping of nodes. Okay, that's why like in the human, there's a critical age for learning. After a certain age, you can't learn anymore. I mean, you can learn, but it'll be harder because a lot of these connections are already pruned away, right? So this taught me that, like, yes, you can perhaps learn better by pruning, but that doesn't really solve the problem of learning. Okay, why do I say that? Because if we just do pruning like this, the environment itself still stays the same. Like, you don't choose your environment. Okay? The training data that we use to prune is like fixes, like Cypher or MNIST or Tiny ImageNet. It's fixed. We don't get to choose our environment. We don't get to adaptively like change our situation. So this is great for like maybe having a smaller neural network. But if we want to achieve the goal of fast learning and adaptable agents, this is not enough. So then I thought, okay, AlphaGo works pretty well, right? Let's see whether AlphaGo, can perhaps learn what they need to learn. Okay. And I created my own environment. Later, I'll show you the environment. So this is a 4-in-a-row tic-tac-toe. And this environment led me to realize something, that if you train it on one, it does badly with a slight change. So this is reward-based learning. AlphaGo uses win-loss reward. This is a two-player game. And after I train it to play like perfectly on one environment, I just changed the brick block of this. Later, I'll show you what I mean by brick block. When I just change the environment slightly, okay, I tried it on humans. Humans can still adapt to the new environment. Okay, I actually made an app for this, and I tested it out on some kids. Okay, so actually not really a formal test. It's more like my friends and stuff. So humans do adapt with this environment, but the AI system just completely crashes. So I realized that actually if you just focus on like reward, like learning a game's reward and so on, you don't really generalize to slight changes in environment. Okay, so then I started to think like, hey, maybe the the way to do it maybe is in memory. So I tried to look more on like how the brain consolidates memory, and I came across hippocampal replay, which means that, after you experience something in your day, you kind of learn from the experience, sort of like during the day itself, you also do hippocampal replay, and also during sleep, you also do hippocampal replay during REM sleep. And then you back propagate whatever states that you have. Maybe your winning pathway, you can back propagate them from the last state to the first state, because we replay them in reverse order. And so this might be, yeah, this is a hypothesis. It's not proven. This might be a way for us to consolidate winning trajectories so that we get to repeat those trajectories again. Okay, actually this has some parallels to, O3. O3, you fine tune on the right trajectories. In some sense, it might be doing some form of hippocampal replay. So if you fine tune on those trajectories, so you learn from that trajectories, you get better at doing them. There have been studies of people, after they sleep, they get better at performing a task. So this could be one reason why. All right, then we move on to my landmark ideas called learning fast and slow. So I did realize that just using memory alone is not enough. Okay, because memory can consolidate the right trajectories. But how do you get those right trajectories, right? You need something to explore, right? You cannot just explore randomly. It takes forever, right? You need to explore in a meaningful way. And so that's when I have a goal-directed neural network here. So if we just give it the start state and the goal state and ask it to predict an action, we can actually sort of guide the neural network to go towards the actions that are most probable by this like fast predictor network. Okay, then of course, if you just rely on the neural network alone, you might get lack of diversity. So I added a count-based approach, which is basically like explore, exploit. You sometimes follow the neural network, sometimes you follow, I mean, there's a formula to, the more you haven't visited a state, you increase the exploration term, and then you have a more incentive to explore those states. So with this way of doing exploration, coupled by a memory-based planner, where you just look through your memory and try to find the optimal trajectories to go towards. So this combination of fast, I call this a fast network because it's just a one-step thing. and a slow look ahead. This combination of fast and slow look ahead, okay, combined together, forms quite a good way of exploration. And then you can use techniques to learn from them, like hippocampal replay, self-supervised learning. I'll go through that more in detail later. So this is something that I was quite excited about. And this was before large language models came out. So after large language models came out, I realized that actually the large language model might be able to replace this. Or rather, you might be able to use a large language model to do some form of selection, like neural network guided action selection, which might actually be much faster than just simply learning from an environment. Like if your large language model already has some biases that it has that can solve the environment, like for example, maze navigation, it might already know how to go from like top to bottom because it has seen 2D grids. You might be able to use this to bootstrap your learning. So I did some work on large language models, specifically trying to solve the ARC challenge. The ARC challenge is like an IQ test where you have grids and then you need to find the relation between your input grid to your output grid. So we have this ARC challenge. And in this thing, I realized that large language models, if you just give it general input to general output, it's actually quite bad. Okay, because it needs a lot of examples to learn. But if you constrain your input to a constrained output or to a general output, actually, it's better. Okay, so I'm not sure if you can see the words here. So what I'm saying is that if we imbue some biases inside the network as to how it processes the data, it generally performs better than just feeding it the whole load of data inside. So, I mean, there's this saying that, learning is about knowing what not to learn or eliminating noise. And this is exactly it. So again, LeCun likes to use latent spaces, abstraction spaces, and so on. So this is actually a case of multiple abstraction spaces. We process things in different spaces like grid view, object view, pixel view. Like, our visual system, we process things like moving objects as one system, color as another system. So we have different abstraction views that can be combined together. And this is great because this allows for you to have more targeted processing, right? And also it allows for compositionality where you can like mix and match your different views together. So just using it on ARC, I drastically improved the solve rate. Like just having, because most people just do pixel view, right? But you put object view, put grid view, different kinds of views to view these puzzles in a different kind of way. It might be easier to solve certain puzzles in different views, and as such, the solve rate improve. Okay, so that's one thing. Okay, so my main aim is to like use this learning fast and slow system, like make it better. So large language models, I experimented a bit. After that, towards the last year of my PhD, and also in collaboration with Symbian, who employed me during my last year, I came up with TaskGen. Right, TaskGen is a task-directed or task-based, memory-based network where based on a certain task, you do the task, you split them up into subtasks, either assign them to other functions to do it or other agents to do it, and gluing all of them together, we have memory that links all the components together. So this is one way of implementing a goal-directed memory-based system. The next future work will be to merge together more of like, how do we do this, plus learn the fast neural network like this? Because right now, if we use this system, it is purely in-context learning. So if we want to do it, we probably need to do some fine-tuning as well. So yeah, I'll talk more about that later. So this is basically some the roadmap of what I'll be taking you through today. And the key thing, if you want to take away from all this, is that a blind pursuit of reward is not going to generalize very well. All right. We will need more goal-directed systems. We will need more memory-based systems to learn faster. So yeah, any questions, thoughts first before I move on to the individual sections? Okay, good. All right, so this is an overview. Now let's talk about the first paper. This is DropNet. DropNet, basically the idea is that, we take any neural network, we initialize them randomly, train it, and then based on those nodes that do not do a lot of activation, like out of all the training sets, like we basically don't have too many things. that are activated based on these nodes means it's probably not that important. We just drop it. Okay, after you drop it, we start with the rest of the section, and then we do the same procedure again and drop the rest of the nodes that don't really contribute much. And then we keep doing until we reach the endpoint, and this is the final network structure that we have learned after using iterative pruning. So, I mean, people ask, why do iterative pruning? It's been shown that if you do this method, it performs much better than if you just slash out all the nodes at the beginning, like from here to here. The performance is horrible. But if you iteratively train, reinitialize, and prune again, it works better. So this paper is actually a variant of the lottery ticket hypothesis by Franco Carbin. Yeah, so he basically pruned weights. So I decided that, hey, why not prune nodes or prune filters? And I've got similar performance to what he got. So if we talk about like pruning filters, all right, pruning filters means like we see which CNN filter has the least average activation and just prune it. If you look over here, these are the metrics to prune by, like minimum activation globally, minimum activation in that layer of the convolutional network. All right, random means I prune randomly. Random layer means randomly prune within the layer. Max means prune the highest activation, which generally not a good idea. If you look here, the performance drops drastically after you prune like 40% of the filters, like 60% remaining, your performance drops so much already. But if you just look at min layer or min, even after you prune so many times until like 90% of the filters are gone, the accuracy is still like within 10%, all right, of the original accuracy. And same thing for here. Like if you look here, like even after you print 80%, mean layer is quite good. This is for VGG 19 and this is for ResNet 18. And what this is on the CIFAR 10 dataset where you need to recognize 10 different objects. All right, so what this shows is that it's possible to get a smaller network by pruning. All right, so okay, that's more or less what I want to cover for this. This is not really the highlight of the thesis. This is more like an exploratory work about pruning. Then I went on to focus more on how we can actually choose the environment that we learn in, or how we learn from the environments. So next is about break tic tac toe. All right, so break tic tac toe is like this. The idea is that you have an environment with a brick, and then this brick block is basically a place that no one can put their their pieces in. So it's like tic tac toe, but there's a constraint. There's a brick over here, and we train the system on variant 1, and we test it on variant 2, where the brick is displaced slightly. All right. So as I said, humans actually can still play quite well with this variant 2. In fact, it should be easier because you see here, you actually have more space here to play with compared to like here with a lot more constraint. Okay. So there's a way to win. Always you can win with the first player. This game was designed like that. So it's just to see like how well you can like generalize. And yeah, I actually have a version of the game that I implemented. So I'm going to share with you the game right now. So let me share my screen with the game. Hang on for a while. Need to load the game. Where's my Zoom? Okay. All right, can you see this screen? Can you see the screen?
Yes.
All right. So I just want to ask like anyone want to try playing the game? So you can just tell me like which square do you want to place in, and I'll place it for you. So this is basically, I mean, I'll just show you like how the game works, and then you can. So we have the rows here as A, B, C, D, E, F, G, and then here is, oops, 1, 2, 3, 4, 5, 6, 7. All right, so yeah, let me just show you roughly how this works. So if you like place somewhere here, then the AI will place back something, and then the idea is you need to form 4 in a row. So yeah, any volunteers who want to try to see if they can win this?
I don't mind going first.
Okay, that please.
Let me play B3.
B3, okay.
Alrighty. C4.
C4. Here. All right.
D4.
D4. This one.
Let's see, E5.
E5. Here. Okay. I think you. Okay. Yep. Can. Still okay.
C5.
C5. Here.
Now, is it 4 in any direction, including diagonal?
Yeah. Point in any direction.
Okay. B5?
B5. B5. This one?
Yes, sir.
I think you had the block, right? Yeah.
Yeah, I'm gonna have to. E3, C2.
Okay, so
Ah,
in this case, there's actually a strategy that you want to try again, or anyone else want to try? Like, you basically need to. Okay, I don't know whether I have to spoil it, but let's have one more try first. Then I'll tell you the strategy that is needed. Anyone want to try it? It's
Can I
okay
have
to
a
lose.
try?
Yeah. After you want to go, yep.
I first.
Yeah, of course. You start first.
Okay. D4.
D4.
C4.
D4.
Oh wait, I made a wrong move.
You want to restart?
Yeah, sorry.
D4 again.
Yeah. C5. Let me see. D3. B3.
I had the block here, right? Yeah.
Yes. E4.
Yeah.
Yeah. Oh,
Yeah.
yeah. Let me see. Maybe B6. B5.
B5.
Yes.
Actually, I think maybe playing the next stage might be easier. Yeah, the without the hole is actually harder for player one. But yeah,
C6.
C6. Yep.
Oh, C3.
Okay, I think it's more or less going to be a draw already with this. Okay,
Yeah.
but so you don't mind?
I just follow a very simple heuristics.
Yeah, what's your heuristic?
So if you are actually, I think it plays into, okay. So if I'm first, right, then after the opponent make a move, I'll try as much as possible to make my next move to be in line within the four steps
Yeah,
neighbor.
you
But
got
at the
it. You
same
got it.
time, trying to block their next move. Yeah, that's just a very simple.
Yes. So let me just show you like let's say if you want to win, what you do is you form a direction that tries to block them. Okay, then next what you will do is you will try to form something what I call an unblockable tree. Okay, which means that this is one track axis. You need to form a second track axis, which is like somewhere either you put D3 or E3. So let's say if I put D3, you see out of this, when I form this triangle here, I claim these three directions. Okay, once I put this X here, actually I claim these two directions here, which is this green arrow, this green line, green line, computer can only block one. And the moment once I form 3 in a row, I win already. Yeah, so this is like, if we go to the next environment also. Yeah, so basically, if you follow this strategy, and I mean, if you just form 3 in a row like that, the AI will have no chance of winning. Okay, you see that you can win already like that. So yeah, I think this one, after you play it enough times, you would know this is actually some strategy about like maximizing your threats. Okay, let me just go back to the presentation because I think this game is quite fun. If you want, I can give you all the link and you can try it yourself. There's more levels after that. Yeah, I wanted to create an entire sequence of 9 planets and so on, but I only did 2. Like after Moon is Mars. Yeah, so if you're interested, you can play the game. It's on simmer.io. I can link the link there. All right, so let me go back to the presentation. Hands up if you can see the slides. Okay, great. So this is the Tic Tac Toe, meant to be winnable as player 1 all the time. Because if you know the strategy that I just mentioned, you will be able to outsmart the competitor. In fact, there's no way for player 2 to win, right? Unless you you fail to keep up that threat, player 2 can actually form 3 in a row and win, all right? Because 3 in a row, you have to block both ends. There's no way to block it for the next move. Okay, so a very, very simple game, but it tests how good your AI system is at winning this game. So let's see how the AI system fares. So I actually trained Alpha 0 for about 1 month in my environment before it could before it won. I mean, maybe I trained it wrongly or what, but eventually it won 100 times out of 100 times against a Minimax agent. So Minimax basically is a tree search where at each branch you select the best move for yourself and for the opponent. So you can go and search more on Minimax. I'm not going to cover much on it. Monte Carlo tree search is a tree search whereby for each move, you have a value of the move that comes from backpropagation of the end state, and you have an exploration count. So the 2 terms add together, you choose between explore and exploit. Explore is the exploration count, and exploit is the value of that state. So Monte Carlo, we can go by 1,000 iterations or 10,000 iterations. So over here, Minimax actually did the best because I gave it some heuristics that, my heuristics are like, if you have 2 in a row, it's certain points, 3 in a row is certain points, and so on. So the heuristics encourage the AI to form 3 in a rows. But just now for the game you saw, I made the heuristic such that it will prioritize blocking the player first before forming the 3 in a row, so as to make a more entertaining game. Because if the AI just wins straight away, it's not very fun for the player. You want to drag out a bit. Yeah, but other than that, there's some strategy that you can imbue inside your Minimax because you have a heuristic score. Same thing for actually Monte Carlo research. You can do heuristics, but I didn't do heuristics for this. So the aim of this is not to show that Monte Carlo tree search or Minimax is better. The aim of this experiment is just to show how good the generalization of Alpha 0 is. And if you look here, Alpha 0 with no search, okay, which means that I don't use the Monte Carlo tree search at all. Actually, it did quite well. It solved 100 times. If I use the tree search, it will also solve 100 times. But here's the catch. If we train it on variant 2, which means that like I don't have any like training on this. Variant 2 is where the brick is displaced a bit. You can see that it loses entirely. Okay, because it tried to use the same strategy, the brick is in a different position, it failed to win. Right? But if you look here, the surprising thing is that methods such as Monte Carlo tree search, you can still win a bit. All right. So actually, in this case, this player 2, right? So like this player 1, like if we look at it, it's actually winning quite a bit. In fact, the more search player 2 can actually win. But let's say Minimax will always win in both environments, which means that actually the heuristic is quite good because like humans coded it, so it's a bit not very fair. But what this shows is that if we are just training for one environment, we might suffer from overfitting, and that reward objective that Alpha 0 has, once the environment changes a bit, like in this case the brick changes a bit, I'm not able to learn that well anymore. Like I'm not able to perform that well anymore. In fact, I might need to train from scratch. In fact, training from scratch also did quite poorly. Yeah, I did not have the experiments here, but it's best to train from a neural network that is completely new to learn this new environment, because it has some inherent biases in the first environment. It might tend to bias certain search path, which may not be that great. So these are some kind of downfalls of doing reward optimization. So I always like to tell people that, optimization is not the way to go for adaptability. All right, you think about it. If you are optimized for a certain domain, like for example, you only know how to do deep learning, maybe. Everything to you is a deep learning problem. Or maybe if you only know how to do logic-based, first order logic, everything to you is a first order logic problem. Then if, let's say, I want you to do something else, it's very hard for you to get rid of that mindset to move to something else because you're too optimized to that one track. So this is a general comment for PhDs in general. So I mean, like, the idea is the same for a lot of things. Like if you are too specialized in one thing, you might not do well if the environment changes. Okay. So there's some saving grace. Okay, actually, I did not want to cover this slide today, but let me just show you the slide anyway. If we actually increase the amount of training distributions, all right, we can actually increase the win rate. So like, for example, if just for default, it didn't do too well, all right? But if let's say we train it under more environments, actually it can perform more. Right here, I actually ran for more games, like 500 games, and I actually trained this AlphaZero for a few months. I can't remember how many months, but I trained it for more than the initial table. It actually can win more and more if we train it under more starting variants. All right. Okay, but it's still not exactly that great. Okay, because we still did not reach 100%. But you can see that if we train it under more variants, it can mitigate the issues of being stuck to one environment itself. So there's some saving grace for reward-based models. Is this thing called domain randomization. Okay, if you have more domains and then you can train on all of them, it will reduce the likelihood of overfitting to one domain. So yeah, there's some saving grace for models like reward-based models. But if you think about it, it just means that, what we need to do is to basically train models that don't just rely on one fixed reward. It's more important, the take-home message is that it's more important to train on the goal itself. In this case, the goal is to win. All right, then in different environments. Okay, then it's better to do that than to train it on just a reward to like maybe win in one environment. So I guess in this case, the reward equals to goal in this case, because winning is your goal, right? But what I want to say is that our goals, we should try to avoid over specific goals. Yeah, and yeah, this basically just shows that if we just increase the diversity of our goals, we can actually learn better, right? And after I did this experiment, I realized that maybe this whole focus on reinforcement learning a reward, can be a bit misguided, because in some sense the reward itself, okay, if you look over here, the reward for winning this game here on the left and winning this game on the right, the reward is actually the same. Like you get a 1 for a win and a -1 for a loss. And I think in this case, it might be a little tough for the AI system to know, hey, why exactly am I getting the 1? Why am I exactly getting the -1? Okay, whereas if we have like natural language, if you have language, it might be easier to express the goal. Like for example, just now I just taught you like how to do the 3-axis thread, right? I use language to do it. If I were to use an AI system to do it, it would be difficult, because if I use a reward, if I give you a 1 when you win and -1 when you lose, you might not be able to win before you get the 1. You might basically, it can be difficult to win, and you might never get your reward of 1. So yes, I can like randomize the starting configuration. You can perhaps try to learn through pure chance how to win, which in this case, it does, because this is a small game. You do 10,000 iterations, you are bound to hit something good, right? But if it's a larger game, it can be difficult to win even with the increased search. right? But with like certain things like language, maybe it might be easier to express your goal. And I kind of realized that, maybe what we need is goal-directed learning. Like if you just give the reward itself, it's really, really very hard to learn. Case in point, if you have a kid, you just give the kid maybe a lollipop whenever he does something good in your opinion, and maybe scold him or her when he or she does something bad. But don't tell the reason at all to your kid. Don't tell. Just reward or punish accordingly, but don't tell anything. Chances are it takes quite some time before the kid realizes, hey, why am I being punished or why am I getting rewarded? Okay, so whereas if you just tell the kid, hey, this is bad behavior because you might injure yourself if you jump off the sofa, that kind of stuff, it might be easier. In fact, it's likely much easier for the kid to learn. So one thing I realized about humans that we do this quite well is that we actually learn from goals quite well. Like why we didn't, then we also do reflection on why we didn't achieve certain things, and then we learn from our reflections as well. Yep, these are all missing from reinforcement learning. Like with just one scalar value of that reward, how much information can I tell you? Oh, great job, you got a reward of 1. Why? Why do you get a reward of 1? So I all along thought reinforcement learning was great until I did this experiment, and then I changed my mindset completely. I realized that reinforcement learning is a bit too difficult to learn from because it doesn't give you much information. Right? It's great to learn robot movements of the legs because you can't really describe your arm being 10 degrees up, 12 degrees up. Very difficult to describe. Sure, it works very well for those kind of movement-based tasks. But for more macro stuff, maybe reward is not the answer. Okay, so I just leave you with this point here because this shapes the rest of my research I did this in year 2. After that, the next 3 years, I've been searching for a solution that they can do better than reward. Right?
Sorry, can I
So you want to say something?
So if you want to express your reward in the form of natural language, the prerequisite is the model must be able to do that in the first place. So using your own analogy, if your kid is still at very early stage where he or she can't even understand the reason you gave, then the only choice you have is to use a reward, right? or punishment.
That's right. That's right.
Yeah.
So in that case, then it will take a bit longer to learn, but you have no other way to train it.
Yeah,
So
exactly. Coming back to here, I think if you want to give reasoning to let model learn from your reasoning, that means you have to use maybe at least supervised learning method or in context learning. But before your model can achieve the level of doing that, like you probably need to bootstrap with RL method first. Then when it reach the stage where it can understand your reasoning, and then you can do that. Also, like I don't see like how you do that. Like you can do reasoning trace, let model to learn from reasoning trace, maybe from in context learning, but in order to optimize the model parameters itself, you still eventually need to come up with some kind of objective function that give you a scalar value. Otherwise, how do you even update the model?
yeah, so there are different occasions where a reward is necessary. And I mean, it's the only case. So I agree with you for that. I'm just saying that for cases where it's a bit more open-ended, where like maybe a language guided search would be better, we should use those.
Yeah, I agree on it.
Yeah. So in this case, actually, if we use language to do this, we can just say, like, after every game we reflect and then just say that, hey, having 2 in a row is actually good, or having 3 in a row is good. So actually that would be interesting to see whether I can use language models to learn this game. Yeah. I haven't tried this, but yeah, maybe let's do that for the next time. I'm actually interested to know whether language-based guidance can actually solve this game. But anyway, this is and just to show that if you just do reward and your reward is too fixed, it's very hard to generalize. And here our goal is fast learning and adaptable agents. So this is not exactly the strategy we want unless we can simulate everything. Okay, so that's what NVIDIA is trying to do. They're trying to use their Isaac system to simulate everything. So I wish them all the best. I think it's quite hard to simulate the whole world. So you might need more things than just simulation. All right, so next we have memory-based learning. And this is a kind of thing that I've been thinking about. It's like, hey, reward so hard to learn from. How do humans learn from experience? And it turns out that a huge part of who we are today is based on our experiences stored in our memory. So the memory is like either your procedural memory, which is like how you play the piano, how you eat, or it could be like more semantic memory, like you store facts about the world, or you store like certain actually emotions play a huge part here, but I did not do much work on emotions, but I think it's quite important because it tells you what memories to focus on. Right? So this is a thing that humans do very well. We do memory-based learning all the time. Conscious or unconscious, you will still retrieve some memories. That's why certain passing by like your old school triggers memories without even you wanting to trigger it. Right? So this can go into the conscious memories, but actually a lot of times this memory retrieval is subconscious. You won't know it, but you retrieve memories on the past to bias and condition what you do right now. So how can we learn effectively using memory-based learning? And here, there's this work that was done, I think 4 years ago. It's called Go Explore. Go Explore also came to the same conclusion as me that reward alone is bad for sparse reward settings where it's very hard to get to the endpoint. So theirs, they actually focus more on the explore, all right? So their goal is basically choose a state that is quite good, go there, and explore is to explore from that state. Right, so there's this game called Montezuma's Revenge. Who has heard of it? Montezuma's Revenge. It's an Atari game that made headlines 4 years ago. Anyone heard of it? Okay, so why this game made headlines is because it's notoriously difficult, right? In order to win the game, you need to collect keys. You need to go to doors. Yeah, I'm not sure whether this is a door, but like you need to go to the door and like you need to avoid enemies. So all this actually for humans, because we know physics and stuff, can be quite straightforward to us. But to the AI sees the game as pixels, and then it tries to generalize how this works. It really cannot do it very well. So what this game did is that they help the AI explore better. I mean, the AI still doesn't know what the physics are, but the AI can teleport. Okay, what I mean by this, all right, you can actually go to a promising state and explore from there. You don't have to start from the beginning. You can just jump to a state in your memory and explore from there. And one key thing that they did is that the state's value of the state and also like the trajectory to go there will be updated if the trajectory to reach that state is better. Like if it's a shorter path, you get higher reward, you update the trajectory of each state in your memory. And this external memory-based system solved Montezuma's Revenge. Okay, in fact, it not solved it, it basically just bulldozed the entire competition in terms of this game. So how does this work? Let's take a look at this torchlight analogy. This is not in Montezuma's Revenge paper or Go Explore paper. This is what I think they are doing. So imagine if you are trying to search the room, you have a torchlight. Your torchlight, maybe you do random exploration, you can only explore this much because any more is too much compute. Of course, if one day, if your compute is huge, you can just random explore all the way from here to here. No problem. Yeah, if let's say we invent quantum computing, we can search everything. Yeah, then you don't have to use this strategy anymore. Okay, but with this strategy, what you do is you have a few states that you explore to, let's say in these red dots. You choose the more promising state based on some heuristic or like your current reward or whatever. And you start from here and you can explore again randomly. And then you store another state here and you store another state here, store another state here. Eventually, because you have bootstrapped from where you have explored before, like for example, if I know there's a trajectory that goes like that, I can just teleport here and then explore from here and reach the goal state. So basically, I get closer and closer to the goal state, hopefully, with the way I select my states. And this is the go explore method of exploring to get your reward. Right? Of course, if your heuristic is wrong, you might go further and further away from the goal. But if you smartly use the right heuristics, you'll be able to get closer and closer to your goal. So I did something similar to what Go Explore is doing, but instead of like doing a random selection across all explored states in a certain proportion, I actually use a upper confidence bounds equation where I balance between the reward of the state the number of moves to reach the state, which is like how efficient it is, and how many times I've visited and selected this state. So basically, this is my exploit term, which is how good it is, and this is my explore term. So I did go explore, and then we just see how good it is. So the thing about go explore is after it reaches the end state, okay, I also implemented an additional thing that go explore didn't do, which is called hippocampal replay. Basically, when it reaches the end state, I don't want it to just update one state at the back. I want it to update all the states that it has transited to say that, hey, this is the right path. So one thing I realized about this is a very curious thing, is that once we do hippocampal replay, the solve rate is very high, much higher, because it already knows the best trajectory is like that. But it stops exploring a lot, in the sense that you can see over here, there's some states that are much better. If we're doing a maze navigation, we might want to travel like that instead. If we do hippocampal replay, we might stop exploring that, because we already have a very high value reward pathway that the go explore algorithm would choose. And this is a good and bad thing. To me, I think it's a good thing, because if we want to just go to your goal here, it's best that you just solve it, right? Rather than you explore like that. Okay, the bad thing is that because you don't explore so much, you may miss out certain things. So let's go to the results for this. So you can see that this environment is quite difficult. If you just randomly explore the maze, a 10 by 10 maze with some walls, actually the maze is what you see over here. This is the maze. Random exploration gets you nowhere. You solve nothing in 100 runs. And we just do the go explore without account-based method to bias the search, you also get nowhere. The moment I add account-based method, I get somewhere. I get solve rate of 100. Okay. And if we just look at explore count, where basically we don't teleport at all, we just explore from the beginning. If we don't do hippocampal replay, okay, you can see that the solve rate is much lower, which means that hippocampal replay, once it finds the trajectory, it just consolidates that trajectory, and you don't really explore much after that. You can see that it takes 4,912 steps to solve, compared to like explore counts 3,094 steps. Okay, which means that you get more consistent performance, but you get less exploration. Okay, so good for some cases. Like I think humans do quite a lot of this also. Like once we have a certain routine, it's very hard to break that routine, even though that routine might be inefficient. Like maybe you have a routine for brushing your teeth. You learn it since young. It takes 10 minutes compared to maybe if you could do it 3 minutes. Yeah, but it's very rare that you will change your routine because you have solved it. Yeah. So this I think is good to ensure performance, but it's bad to explore. So in humans, actually how we solve this is we have a lot more humans to compare to. So if you see someone doing something better, maybe you will change what you do. All right. But natively, you might stop exploring once you do hippocampal replay. But there's also one downfall about this method of hippocampal replay that I use here, is that because we are doing only the memory updating for one final goal state. So if we look back at this maze here, the start state and the end state are the same. Start state, end state, always like that. So you can hard code, you can memorize your start state to your goal state. And actually this hard coded or this memorization to game benchmarks is also happening in LLMs right now. You basically get access to the data of the benchmark, train it on it, and then you can say, hey, I did very well on it. But you sort of memorize the benchmark. And I don't think this is the right approach. Like, so after I did this hippocampal replay paper, I was actually quite excited at first. I went to NeurIPS to present it. Before I presented it in NeurIPS, I talked to a few people. I met quite a lot of nice people there at NeurIPS. I realized that this is wrong. So it's very funny, right? I'm supposed to go to the workshop to present this, and before I presented it, I realized this is wrong. All right. So why I say this is wrong? It's wrong because it's too fixed. In the real world, you're not going to start from the top left and go to the bottom right all the time. What if I want to start from the bottom left and go to the goal, right? Okay, in this case, it's still easy because I just need to hit the exploration pathway and then, hey, I'm good to go, right? What if the goal changes? What if the goal is here now? All right, whatever I learned about this goal here, you see, this exploration highway exists regardless of end state. So like your reward is always, the trajectory is always to this goal. If I were to change the goal, unless what I do is I have a separate memory that can store different endpoints. Yeah, I mean, you could do that. It's just very hard to, generalize to the goal state like that if you have a separate trajectory for each end state. Like you have to learn 10 by 10 end states. Like that's quite difficult. You could use a neural network to do it. And that's the key thing. You could use a neural network to do it. And this is the basis of goal-directed learning. What if we don't just store trajectories to just one endpoint? What if we store it to an arbitrary endpoint, right? That, you could either access it through a neural network or you could search through your search space. And one key thing is we don't use reward just to one goal. Okay, we don't just use this. This is very important. If you take away one thing from this session today, don't just use learning from one single goal for your reward. Okay, if you are using reward, use goals directly, like alter your goals, learn from your new goals. Okay, because this is very important for adaptability. We don't want to just be fixed to one goal. What you see here in this hippocampal replay work and what you see earlier in the break tic tac toe work, if we just have only one goal, you change the goal a bit, your whole system will crash. Okay, this is not shown here because I did not do a change of goal, all right? But I'm quite sure if I change the goal, the system will crash also, all right? So this was great to highlight that hippocampal replay can learn stuff, but we are still missing something apart from this learning. We are still missing the goal-directed component, and that's where the next paper will come in. Okay, so this is the highlight for my PhD actually. Like I really spent years thinking about it. I read countless books on neuroscience, psychology, biology, cognitive science, and so on. And I struggled to find a method that can actually learn and generalize. And eventually, I thought of this. Yeah. So this is the goal-directed memory-based learning. I call it learning fast and slow. So this received the best paper finalist in the IEEE ICDL. It's the International Conference on Development and Learning. So there's some merit to this. And right now I'm working on trying to imbue this more with LLMs to make it work better. So I'm still thinking of ways to sort of update this architecture in modern times. So still thinking about it. As you know, good ideas take a while to come by. Hopefully, if you all have other ideas, you can contribute as well, make this better. So this is reinforcement learning. I realize I spend a lot of time talking about reinforcement learning, but I haven't really explained it. So reinforcement learning is you have a state, your agent will take an action in the state, the environment will give you back a reward and your next state. So it's like, this is reinforcement learning in a nutshell. And reinforcement learning is very slow to learn. Very, very slow. So if you look at how the typical Bellman updates are done, it's based on this thing called the temporal difference target, based on what the actual state is versus what you think of this state, you update your difference accordingly. So basically, if we have this transition that goes to the door, I will update that. Okay, maybe you have a discount factor. Maybe the discount makes the end reward is 1, the discount factor is 0.9 maybe. So I update this state as a value of 0.9. And you only update one time. Okay, so that means you need to be lucky in your updates to update all this again. So like, for example, if this path is 20 squares long, you need to have 20 different occasions to update this 20 times. All right, the same thing for Q values. Q values is instead of just having a state, having a value, the Q values are pegged to actions. So it's a state action value. Okay, so both are similar actually. It's just that one has an action inside the value as well. So it's very slow to update this. If you look at methods earlier, like deep Q learning, they have a replay buffer that randomly selects the experiences to replay, and hopefully you learn the transitions. takes too long. After that, we have methods like proximal policy optimization, which is better because it learns from the whole trajectory. So I would say that reinforcement learning has improved. In some sense, PPO contains some form of memory replay already, because it learns the rewards backwards from the trajectory all the way to the start. So that's why PPO is quite good. So reinforcement learning is very, very slow to learn, and it suffers from one thing which I said earlier. You change the goal state, you have to learn from scratch again. Yeah. So this is something that, because we learn from reward, we don't exactly see the full picture. It's like, you have X different configurations of an environment. You only see configuration one. That's not enough. You need to see the rest also. And just looking at the reward, you won't be able to tell which configuration your environment is. Only when you target the goal, you target the end state, a goal-directed kind of learning, can you generalize across to different goals. So this is the insight. So goal-directed prediction. So this is something that is quite curious also, because in humans, this is what we do. Let's say you want to navigate from your house to a shopping mall. You have no idea where the shopping mall is or where the tower is, but you can see it. All right. Now everyone wants to create like super intelligence. We don't know how to get there, but we can see how it looks like. You are able to sort of approximately head towards there by some form of prediction. Okay, in this case, what I recommend is that we do action-based prediction, because you can do self-supervised learning. Okay, I'll explain how later. So self-supervised learning is superb. It's way better than supervised learning. Okay, because supervised learning is like, MNIST data set, you learn how to classify digits 0 to 9, or the CIFAR data set, you learn how to classify objects. But the moment your objects change, or the moment your digits change, you have to learn from scratch again. Self-supervised learning, you don't have to do that. Self-supervised learning, if you predict like an action space, okay, in this case, it's an action space because we are moving. But in the case of MNIST and the objects, right, maybe you can predict some form of language characterized latent space. So I mean, that's what like stuff like the diffusion based models are doing, language condition latent space. Yep. So this kind of learning are much more efficient because it can change according to your goals. All right, self-supervised learning, in this case, if I have my start state and my goal state and I predict the action, I can basically change my goal and I can learn a new action. All right. And the good thing about this is that because when we go through a maze, we have this state 1, action 1, state 2, action 2, state 3. So this actually like this is called a trajectory of actions and states that you yourself have taken. Like for example, if state 1 goes to this square at the bottom, state 1 is here, action 1 goes down, and then action 2 is go down, state 3, and action 3 maybe is go right, and then here's state 4. The good thing about this kind of self-supervised way of doing action-based prediction is that you know that you are the source of truth. You have traveled there. You definitely know you can reach there. So whatever you learn based on the start state and goal state, you predict the action, you definitely know that you can reach it. So this is great because we can learn from your own experience. We don't have to have an oracle. You can learn directly from your own experience. So a lot of key insights here. We use heuristics to head towards the goal, and we can learn from our own experiences to basically refine our prediction model. Memory. Okay, memory is an interesting thing because a lot of people have tried to do world models. And I'm saying that world models, I don't think it's possible. Okay? The real world is just too messy to learn a model of. And more importantly, we just need to match states that are similar to what we have, similar to what we have seen before. So we remember what we have experienced and retrieve it a second time. So for example, if let's say you have a certain state like state 1, you take an action A and you go to state 2. Next time if you want to go to state 2, you can just go to your memory bank, maybe do some rack or something. Now we call it rack, retrieval augmented generation. Like you can just do some form of retrieval based on similarity to what you have seen before, and you can get your transition already. So we can use this to mimic a world model, approximate a world model using memory consolidation, and retrieval. So I don't know whether I'm the first to think of this, but I think this is something that I've been thinking about a lot because there's this model called Dreamer V2 DeepMind models. They basically try to learn a world model. They take insanely many episodes to learn it, and the world model is not even accurate. So I've been thinking about this, whether a neural network should be used to learn a world model. I still think the answer is no. So yeah, I mean, I seek to correct my view on this when the world models are better, but right now is no. All right, it's better to use some form of memory, condition on those memory, and learn from the memory. So this is the overall architecture of fast and slow. We have the goal-directed model here. Then given the state and goal, choose the action. We have a memory-based planner here. Given the state and goal, search through your memory in whatever way. Here I just do random exploration. Randomly go to the next section, take from memory whether there's a next state, and keep traversing the memory until you reach your goal. Okay, and then you can do it in parallel branches because in the brain we have mini columns in the neocortex. In the neocortex, maybe these mini columns are doing some form of trajectory prediction. They just simulate mentally your various trajectories, and then if one of them reach the goal, well, yeah, okay, we know your action to take now because we have in memory something that can reach the goal, and there we have the action here that can be used to override your fast prediction here. So this is the neural network based fast prediction. This is the slow memory retrieval that simulates the look ahead. Okay, to look ahead the trajectories and choose the best one. So in general, this is how the system works. Okay, of course, right now we could potentially improve it by putting in LMs at both sides here. You can put in LMs to retrieve here. Sorry, put in LMs to help to retrieve the memory, put in LMs to help to do action prediction. So possible to integrate. So let's move to this very impactful slide here. I think Derek has seen it at least 5 times. So, so this is a slide that kind of, how do I put it? It's something that I view this strongly about, okay? About hippocampal replay not being about reward. Okay, so the traditional view in neuroscience is that, the mice goes through a maze from this orange circle to this purple circle. During the time of it traveling, okay, it actually remembers where it has visited to, and in its brain, it actually replays forward and backwards. Forward replay and reverse replay. All right. And also, not just what it has traveled, it also does a replay of what it is going to travel to. Can you see that the mice brains also travels to purple circle and back? Okay, so the mice has not reached the purple circle, but in the brain itself, the replay is both the stuff that it experienced before and the stuff that is planning. So quite curious, right? Why is this happening in mice? All right, and this is my hypothesis. I don't think it's learning the reward model for this because if you look at studies have shown that mice will explore maze without food. Okay, so usually people like Skinner, famous psychologist who thinks that everything is based on like you need to reward behavior. So he has cats in the box and the cats needs to get out of the box and then he feed the cat something. Yeah, so famous psychologists like I think BJ Skinner or BF Skinner, yeah, have long assumed that reward is the key motivating thing to why we do things. Okay, this is not the case. All right, people will do stuff without reward as well. Okay, let's look at you over here. Coming over to listen today. I'm not giving you any money. You are just here to listen because you are interested in something, and maybe that's your reward. I mean, people like to say intrinsic, extrinsic reward, and so on. The main thing is reward is not the key factor as to why we do certain things. Okay, likely what we want to do is we have an internal model that creates a goal and we just do the goal. All right. So we head towards the goal. Given our current state right now, we try to go towards the goal and we take an action right now. So like, for example, if I'm hungry, I need to go to the fridge to, take some food. My goal is to go to the fridge. My current state is me sitting right here. And my first action would be getting off the chair. right? Or walking towards there. So a goal-directed neural network, I believe, is far superior than a reward-based neural network, because you can represent, I mean, certainly if you only have one goal, you can represent that goal as your reward. But if you have many, many goals that keep changing, it can be very difficult to explain this as a reward, because your reward is just a number. Like, how are you going to explain that, hey, this reward is for the goal being at top left, this other reward is for your goal being at top right? Very difficult. Okay, unless you put that in the state. Yeah. So this idea of hippocampal replay being a previous state's replay and a future state's replay, it's very, very important. Why? Because you not only learn from what you experience, you also learn from what you have experienced before in the past. So this is what the mice have experienced before in the past. Okay. Either they did this experiment many times until the mice has seen this purple one, that's why they know that this state can be decoded. Or using the previous experience the mice has, the mice generalize the previous experience to try to plan towards this purple one. So this is what the mice has experienced in the past. This is what the mice have just experienced. Okay, so this, I try to simulate this out in learning fast and slow. I try to mimic this learning pathway. So this is the key insight. If we have a certain trajectory, A map to B map to C, all right, which in this case, like this is A, maybe somewhere here is B, and somewhere here is C. Okay, to contextualize things, all right, let's just give it some example, all right? So for example, if A is like, like you are at school, and then you maybe take a bus, and then you go to supermarket, and then maybe after that you go to, I don't know, supermarket and a mall, all right? So if let's say you have 3 states here, this is state A, state B, and state C, and the action here maybe is like from school to supermarket, you take a bus, from supermarket to the mall, you walk. If we have a certain trajectory, A, B, C, and you have done it before, you know how to go from school to the mall. Okay, you know how to do this because you know that the first action is bus and then the next action is walk. So if you give your neural network A as the start state and C as the end state, you can predict bus. Likewise, if you give your neural network supermarket as your start state and mall as your end state, you can predict walk. And you also have one more thing here. If you give school as your start state and supermarket is your end state, you can predict bus. So can you see that just from this trajectory, A to B to C, I have 3 streams of experience that I can use to learn, to train my neural network model on. And I think this is very efficient because, I always like to tell people this. I say, if you want to reach your handphone, all right, and you fail to reach your handphone, does that mean you learn nothing? Because in reinforcement learning, you learn basically nothing because you don't get a reward. The thing is, if you model this 3 cm from your phone as a goal, I've learned how to reach 3 cm from my goal. And then maybe in the future, I can simulate from 3 cm to the next one, how to go there. Something like Go Explore. Okay, but we don't use only one goal for Go Explore. This goal state can be arbitrary. You can reach 3 cm from your phone, 5 cm from your phone, and you don't even need to give a goal state in advance. You base on what you do, you correct accordingly. That's why like basketball players, if they miss a shot, right, they are able to calculate, how much offset the shot actually did and correct for that offset in the next shot. Because they learn from the goal, which is like, I want to reach the net, but I miss a bit. So maybe I should use a bit more force to go towards the net. So we learn from error feedback. And this is in large part helped by this goal-directed learning, because we have a certain goal, we fail to reach it. Maybe we change our strategy accordingly. And I think this is a thing that I want to emphasize a lot, because I don't really see this being done. Maybe O3 uses something like this to learn correct trajectories by splitting the trajectories into subtasks and learn from start to a certain subtask, or from subtask to the end. Maybe it does that. But I find that if you use this way of goal-directed learning that learns from any arbitrary start point to any arbitrary endpoint, and you just learn the next action, or you learn the whole trajectory of actions. I mean, right now, this was done before ChatGPT came out. Maybe here you can have action plus states trajectories. You could predict your entire trajectory, and over here, you could also, instead of your state, you could do previous trajectory to current state. So you could train it on more information than just one state itself and one action. You can perhaps train it on the whole trajectory and output the next trajectory. So you could do this. There's some work that tried to do this. It's called decision transformers. And it did pretty well. So maybe this could also be your world model if you think about it, because you can sort of predict how your next state would be if you predict trajectories here. So, but the idea is, regardless of what you predict, and like the main thing is, based on your experience you have so far, you should make the most out of your entire experience. You should take whatever state you have, okay, and whatever state you want to go to, and you predict the action. You do that for as many combinations of your data as possible, because you only have one life. You can't experience everything. Right now, deep learning methods, especially for robotics methods that use robots, they don't really collect much data. In fact, very little data at all. That's why I need simulators to augment it. Self-driving cars, also not much data. I mean, you can drive your car in all conditions, but there will always be some case that you cannot predict. So it's best if we are able to sort of predict our next action in this composite form, where based on your whole action trajectory, you are able to learn many things just from one trajectory alone. Okay, so that's for this goal-directed neural network part. I spent quite a lot of time here because I think this is important. You also can repeat the same procedure here for your future predicted memory, because if you are able to predict this memory here, then you are able to, you are able to, how do I say? You're able to also consolidate the pathways to the end goal itself, right? Because like not just what you experience is important. If you can plan to reach that and you already know the plan based on your previous experience, also quite good to consolidate those experiences. Okay, maybe I just pause here for a while. I don't intend to cover all the slides today, because I think this is the main thing I want to focus on. Any questions or comments on this?
I would like to ask some, like this. You mentioned you have some comment building world model from memory, right?
Yes.
So I just wonder, like, how does that help? Because deep learning is already good at the task it has been trained on, which in this case, I guess, translate to if you use a deep learning based RL agent or whatever agent, then I think we can safely assume it is going to perform well in the experiment, in the environment it has experienced, right? Which is exactly your memory. So the difficult part is, how do you generalize to unseen environment? But your memory by definition is all the seen environment. So how does that help?
In this case, you want to do unseen environments, you will need to have some form of exploit thing to get the new experiences. And so in this case, just doing the action prediction alone, you're right, you can't get all the kind of experiences. So you need to have some exploration bias here to choose other unexplored actions. So indeed, this memory itself can only be as good as what experiences that you have. And also, if we talk about multi-agent systems, you can learn from other agents. And actually, humans do this very well. We learn from each other all the time. So I think this helps to solve a bit of the exploration problem.
I see. So you mean like learning from other agents' experience or memory?
Yes, correct.
I see. And I guess it's helpful for failure modes like catastrophic forgetting, right? Yeah, but it's still about the sink environment.
That's true. There's no way to know what you don't know, right? So when you face something that you don't know,
There's way. It's just this is about generalization, right?
Mm.
Yeah. Generalization is about to do well on unseen environment.
That's right.
Yeah.
Yeah, so I think if you are talking about like the earlier environments that I did, like for example, if you talk about the maze earlier, like this kind of maze, if you use the goal-directed method to learn, you'll be able to generalize better to changes of the door because the XY aspect of the maze is the same. Like it's just a variant in the kind of
But you didn't use any memory-based technique here,
correct.
right? Oh.
So I'm not saying that this is the only way, but I'm just saying that this hippocampal replay of states to output the actions, I think this is very important. In fact, I think this is something that I want to see more often. Okay, I don't really see this much, except in large language models. So people might not already know it, but they are doing goal-directed learning in language models. Let me explain, okay? So that's why I love language models so much. Like it feels very natural to me. Like what you can do is like you can do a task. Task is like, add 1 plus 1 or add plus 1 plus 1, okay? This is your current state. 1 plus 1 equals to 2. Solve from here. Right? So then the solve might be like, okay, so 2 plus 1 equals 3. Hence, answer is 3. So, I mean, if you give a large language model with something like this, you have done some partial stuff, and then you ask it to predict the next step. Essentially, this is goal-directed learning because you give it the start state. Sorry, the start state is this one here. The goal is here. And then you ask it to output the action trajectory, which is this one. Okay. So I realize it's all the same color, so I'm going to change the color a bit so that it's easier. So this orange one is here. And this red one is here. Anyone can tell me what does this look very similar to? What kind of architecture is this? Start with A. Current LLM. Okay, agentic framework. Okay. So our agentic framework right now that we have predicts the next subtask, does it, and then see whether you need to do more subtasks and so on, more subtasks until you reach the final subtask. So if you take a look at this thing here, this action could be a subtask. This state could be your initial context of your model. This goal here could be your task you want the model to do. So back when I came up with this, we didn't have agentic systems yet. We didn't have this kind of way of doing things, but it fits very nicely with this goal-directed network. And that's why I like agentic systems so much. It's very natural to extrapolate from here to the agentic system. What I think needs to be done is that we don't learn enough from our current trajectories in the neural network. We can actually can learn from intermediate to end state or start to intermediate state. We don't really learn all this yet. And I think this would be quite impactful if we can do this kind of general learning. Okay, all good. So I just want to touch on a bit on the memory network. So this memory network is basically random exploration. We basically simulate many things. So we start with this start state here. We simulate out the memory trajectory, and then we consolidate our memory here. So what we do here is after we simulate out the memory. So for example, let me just draw a grid wall. Okay, my drawing is not very good, but let me just draw a grid wall. In the first grid wall, maybe you explore like that. In the second grid wall, you explore like this. In the third grid wall, maybe you explore like this. And maybe this is your end state. So in this case, your second column has reached the end state, and you know your first action is right. So what I believe is because, in the brain, we don't really do things in sequence much. Most things are in parallel because our brains are really slow. Action potential is, I think, 70 milliseconds. Like if you want to do a lot of action potential in series, you will die before you do any action. Right? So we will probably do things in parallel. And what this means is that we probably can simulate many possible futures by just running each simulation in parallel. And I get a bit of sore throat here, but the idea is this memory retrieval network just does things in parallel. It searches the search space in parallel, and then based on this search space, it just finds the best search space and use it if it matches the goal. So in some sense, this is multiple sampling and filtering. So this works very well for like Arc Challenge. You simulate multiple possible solutions and you choose the one that works well. And this is what is done in O3 as well. So actually, if you think about it, O3 and my thesis share many similarities. That's why I think O3 is somewhere along the right track. I just don't think it has reached everything along the right track. It's just somewhere along the right track. And yeah, there's a lot more things that we can think about. And you can look at my O3 video for more of the stuff. But this memory retrieval network is just using a memory to do planning by simulating trajectories you have experienced before. And if you have an action that you can take based on that trajectory, we will value the action more than your fast neural network prediction. Because the fast neural network prediction is approximate. This is based on the neural network prediction, approximate. But if we use the memory-based prediction, it is more accurate because you have experienced those memories somewhere before, right? And the math over here, a bit complicated, but the idea is we use the fast neural network, get action probabilities for your goal state. This is your exploit value. And then after that, what we do is we do the num visits here, which means that the more you haven't visited a certain state, the more you want to visit it next time. So this is basically a upper confidence bound equation again. So this is what you get from your fast neural network. Your slow network will use the memory prediction to do multiple look-ahead simulations. And it just chooses like maybe the shortest path that reaches the goal. And it will override the fast neural network if needed. Okay, so this is what I talked about earlier. This is very important. This is not done in current systems much. I think this needs to be done urgently. Memory update. We don't learn in a vacuum. We don't learn in a static environment. Things change all the time. We need to update our memory and learn fast. Okay. If we just update the memory based on like, if we just update the memory based on this probability here by the neural network, good luck. You will need like 1,000 to million transitions before you update this properly. Okay. What we will do is we can update the slow memory pathway, which is the transitions here. We can update it with the new transition, remove all memories that conflict with the current transition. Okay, what this means is like this. If let's say you from cell 1, you take action right, and you go to cell 3. Right now, if you take cell 1 and you go action right, you go back to cell 1 because you hit the wall. What we'll do is we'll update all these transitions here. So basically, this thing is no more. We will delete away this transition. We will focus on this. And so this is what it means to be able to, learn instantly. The moment you see something bad happening, you update all the transitions that conflict with it, and you like sort of override it so that, we are able to get this instance all the time. Okay, this was my thinking last time. Now I'm thinking is you can actually keep the conflicting memory, but decay it more. So like maybe all memories can have some like accuracy value, and then maybe this accuracy value will now be like 0.1 or this is 1. So based on the accuracy value, you can selectively, retrieve stuff. So, there's always this saying that, your memory never truly is forgotten. It's just how hard it is to retrieve it. So maybe we can still keep this because like, in the future when the environment changes back again, we kind of want this to rise up again. If let's say this is true again right now. Like, for example, roads, you drive on the road, and then one day you see a roadblock here. So, okay, maybe you need to go this path now. But you maybe you still want to keep your original memory somewhere there, so that in the event that this roadblock is gone, okay, you can like learn much faster because you have some idea of how to go here already. So yeah, I'm still updating my understanding of this. In fact, I would say that my thesis is really just the beginning. I'm still thinking a lot on this. Every week I'm reading books on memory. I think we haven't really found the answer yet. Still searching for the answer. So happy to discuss more if you have any bright ideas on how to do this. The main thing is we need to do memory update. We need to update our understanding of the world instantly when things happen. And that is not done right now in current neural networks. That is what's missing in LLM structures. And that's what I'm intending to focus on. How to learn adaptively very fast through just changing this memory. Okay, I think we are more or less reaching the end for today's session. But okay, yeah. And do you want to say something? Yeah.
Oh no, John. Yeah, thanks for your sharing. I've learned a lot from this. Okay, the question that I like to ask is that this goal-directed concept. How do you think this can support this AI for humanity? Is
AI
that some thought? Okay, I mean, when I say AI for humanity, I'm looking at actually AI ultimately trying to drive towards the good outcome, because your goal concept is actually how people look at it from a purpose point of view. You create certain purpose, drive towards that purpose. Is there something in there that we can think of that direct people towards a good outcome rather than, if you look at today, AI can be used for capitalist outcome, drive towards greater divide, and so forth. Is a goal. This goal directed approach, is that something in there that you can actually look at driving this sort of behavior?
Yeah, so definitely. I think this goal-directed behavior, essentially your goal itself, you could even put some stuff like maybe your initial state you can condition on like good for humanity. So I'm actually quite deeply interested in doing good for humanity as well, because I feel like a lot of these AI systems can be exploited.
Yeah.
And I do agree that with increasing technology capabilities comes increasing responsibility. Just going to be hard to regulate. But if let's say you want a network to do good stuff, one way is to condition either the state or the goal based on that condition.
Yes.
But it's unlikely that your neural network will do it all the time. So the best way to do it is to constrain the action space.
Yeah. Okay, years ago, actually about 10 years ago, I started this thing called Giving.sg in Singapore. I mean, it doesn't use AI and all this, but the whole idea is that through breaking things down into micro actions, you drive behavioral change. And then over time, as people give to, when I say give means it could be time or whatever, it creates a purpose in people's life. And then as a result, it opens up the mind, make people actually more receptive to support each other and so forth. That was actually the 10 years ago. Without all these technology, I actually wanted to build something like that. And we started about 600,000 users now on Giving.sg. Sadly, it is still moving very transactional based, but I find that what you're doing here with the self-directed learning and all that, there's a lot of potential to actually move towards that. Of course, one of my concerns, even when I was building Giving.sg, I actually asked Lee Kai-Fu Lee, in one of the forum, that if I do this, am I actually playing God? Because indirectly, I'm actually putting biases into the model to actually drive towards the behavior that I think is good for society. But not everybody actually can define what is good for society. So I find your model actually is very interesting. The question now is how to actually bring it to that level that then the whole ethics thing brings to an actually different level. Who actually decides that? Yeah.
I understand. This is a tough problem to solve. Like I think this requires quite a lot of discussion and consensus. I mean, even companies and countries are having difficulty in agreeing what is good for humanity.
Yes.
But one thing is, if you are building these models, just don't put the action spaces that can be harmful, like fire weapons, that kind of stuff. Yeah, I think as long as we can restrict these AI systems to do only stuff that even if they output poorly, they don't harm much of humanity, I think, or don't harm at all. That's the main thing.
So your model is very interesting, because I feel that regulation going forward has to be built based on outcome and goals rather than the path. Right now, actually, a lot of the governance are built along the path, which with AI, I don't think it's the correct model anymore. I mean, there's the old industrial revolution concept, but now the way to regulate should be based on goals and outcome rather than the path. which is what regulator has to start thinking of.
Yeah, definitely. I mean, if you apply this model on a macro state, this will talk about macro goals, macro policies, like this actually can apply to any domain because
Yes.
your
Yes.
action can be either transit a maze or it could be making a policy decision. Yeah, definitely.
Yeah. So it's very interesting. I find this. Thanks for sharing. Yeah.
Yeah, no problem. Yeah. So I have a question asking about like, is this different from reinforcement learning? I think Karen, you asked. So it is. Actually, I spent my entire PhD trying to think of something that can do differently from reinforcement learning because reinforcement learning, what would be done is like this. You will have a value state or a Q value state, and you try to, learn the transitions to reach a goal state like this, a reward of 1. But, if your goal state changes somewhere here, all your reward values here are meaningless because now your goal is here. You need to learn a new reward value and so on. So why not just learn by start state and goal state and take an action? And that's basically the idea that I have. And I find a lot of parallels between this idea and the current state of AI agents. So I quite like the current thing right now. So Karen, I hope that answers the question. Okay, so I think today, in the interest of time, I can't cover the rest, and I don't also want to do justice to the rest of it, by explaining more. But let me just end off fast and slow here, because I want to just show you the end result. Fast and slow just says that, if let's say I have a start state and end state, and I randomize my start state, randomize my end state, this is super difficult, I tell you. Current algorithms cannot do this very well, even for a fixed wall like this. I made it even harder. I said, you know what? Real world it's not fixed. Real world changes. So after 50 episodes, I changed the wall, make it even harder for the agent to navigate because the agent needs to forget what it has learned about this and learn this new thing. Can the agent do that? And it turns out that, yes, it can solve quite well. So for this dynamic maze, it solves about 91% of the time. And you can see all the other reinforcement learning methods when trained online, which means that you don't have like 1 million runs to familiarize yourself. Every single episode is a test episode. Like you start from scratch and then every episode I test you already. 61% for PPO. And PPO is one of the best RL algorithms out there, right? You can see that fast and slow also learns a very, very optimal, like 1,700 steps compared to PPO's like 4,000 over steps. And all this I train with stable baselines tree. And which means that these are good implementations of these algorithms. And this shows that, RL methods still have a long way to go for such adaptive learning environments, right? And there's also some form of optimality in fast and slow in the sense that when we select memory retrieval, we select the shortest path. Essentially, we are optimizing towards a shorter path towards the goal already. You contrast this with O3, select short of correct trajectories. I'm not sure whether they select short or not, but like let's say if they select shorter ones, the act of planning to reach the trajectory and also like, actually doing that trajectory so you can learn from it, you might actually already bias towards a more efficient goal reaching, even though it's not explicitly optimized by reward function. The way you choose your trajectories is optimization to an arbitrary goal. Okay, note here, we do not seek to optimize reward to only one goal. We want to optimize goal reaching for all goals. And the way to do that is not to have any reward per se, but maybe you can just select shorter trajectories to your goal. So in some sense, there's some implicit optimization already over here. Okay, just want to add on, this is my last slide for today. Can we increase more of the search depth or search breadth? All right, search breadth means I search more trajectories, I simulate more trajectories. Search depth means I increase the depth of how far I look ahead. Increasing depth, as expected, increases the solve rate. Increasing breadth also increases the solve rate. So both are good, but one thing is increasing breadth finds the optimal path more often. So if you contrast this to the ARC challenge, increasing the sampling to solve the problem might help to get better and better solutions. And then if you can learn from those better and better solutions, you might bootstrap again and learn even better solutions. So essentially, this whole thing, RL is about optimizing rewards, right? But what if we have a new way of learning where we can optimize trajectories towards arbitrary goals? It's not really optimized here. It's more like select shorter trajectories. Yeah, maybe that is enough already to do like almost all tasks. We can do away with this reward per se. We can just select what we learn, and just by training on what we have learned, storing them in either neural network-based memory or like database memory, like the slow network uses transitions as a line item for each memory. When you learn from those trajectories and you store them either in the fast network or the slow network, maybe that's enough for fast and adaptable learning. So I leave it as that for today. I do want to have like 5 to 10 minutes for discussion. So I just briefly highlight what I will be covering next week, because I have stuff like ArcAGI. This is about using computer programs to, like, it's a neurosymbolic method, convert grids into Python programs to run it, and I give it different abstraction spaces. And the more abstraction spaces, the more the solve rate. And then this is TaskGen, which is basically using an agentic system that has goal-directed learning, and it can actually solve the maze. Just now you saw a dynamic 10 by 10 maze. This solves a dynamic 40 by 40 maze 100% of the time. But there's some caveat. I actually imbue some knowledge in language to the agent. So if you can imbue this kind of language to your agent, it will perform way better than the exploration-based methods, because you don't need the agent to explore if you are doing a certain task that you already know. All right. So I'll talk more about this next week. And this is Agent Joe, which is basically what I'm intending to do: multi-agent learning, agent wrappers, more memory abstraction spaces, and so on. And yeah, basically that's more or less it for today. I'll add more slides for this, because I do think that this learning fast and slow is the main thing for my PhD thesis. I think there's a lot of extensions to this. Using large language model is one of them. But the idea of being able to choose your trajectories, being able to do goal-directed learning based on the action space of your trajectories, and this goal-directed learning can be any slice of your start state and goal state. I think this is the highlight of the thesis, because this enables much faster and much adaptable learning. So with that, I will end whatever I want to talk about for today. Any questions, comments, discussion? Yeah, this is the time. Yeah, feel free to say anything that comes to your mind. Anyone? Yep, Derek.
Yeah, I just a couple thoughts about earlier. Which slide was it where you're talking about the memory? I have to remember. It was specifically about like integrating memory into the replay system. You had a slide about it, about like how people aren't integrating it enough right now. And I was wondering about it because I'm trying to read through this paper. I haven't had time to. It's a recent release. It's under Titans. I forget which company released it. You might be familiar with it. The whole
I heard
basis
about
of, yeah, memorizing at test time. And there's a lot of papers that have been covering this whole test time thing, memorizing at test time, learning to learn at test time, and training parameters that specifically have these constrained purposes, such as memorizing important tokens that will assist with faster learning and faster problem solving. And it has a lot to do with the reasoning tracing as well. So I was just wondering about how you would more envision integrating this memory system. Would it be more at the parameter level? Would that be part of the optimization? Integrating the neural memory systems and token systems, and having it work inside of the symbolic framework as well, and having a memory system at the symbolic level, the data line level that you're referring to. The advantages of integrating both of them to work together at the same time, or if one is better than the other, preferably or possibly. What do you think the best path forward is on that?
Yeah, so you just mentioned like 5 or 6 approaches in one. I think right now, memory updating based on this external memory is something that I'm focusing on because it learns faster than the neural network-based memory. So what I intend to do is like you have multiple abstraction spaces for memory. And what we do is like, let's say, for example, you learn from one experience. Maybe this experience is better for like a knowledge graph memory. You just put the instance in your knowledge graph. Maybe one instance is better for a certain memory, like doing first order logic. So maybe you just put it in that memory. Like there's different. I would say that there's no one true general space to do everything. Every single problem has a space in which it's solved most efficiently. You can ask mathematicians for that. Most major theorems are solved because people stop thinking in the usual space to solve it. They think it in a different space and they solve it. Yeah. So like so this is the idea is to give yourself more spaces to do the problem in. So one of them, also more chance of success in any space or any combination of space. Yeah, so like there's this mathematician that solved Fermat's last theorem. I think he did a mixture of physics, math, and everything all combined to one theorem. So the thing is, there's no one space that can solve everything. You will likely need to use the reference frames of everything, of as many reference frames as you can. And so the question is, do we learn this abstraction spaces, or are they inbuilt? And actually, I've been reading some books on memory right now. I think some of the abstraction spaces are learned through environment. Like we learn how to recognize like horizontal lines, straight vertical lines because we see them in the environment. But the structures that we use to decode like the V1, V2, V4 networks, they're already built in by the genes. So structure is predefined, but the neuron connections can be learned. So like how do these neurons relate to like knowledge graph, first order logic? Certainly we don't have knowledge graphs in our heads and everything. But the thing is, we don't really have to follow what the brain does because we kind of are quite poor with memory. Like if we can imbue with more of this kind of artificial memory systems that can actually solve the task that we are more interested in. Like some people like first order logic. Some people have asked me to collaborate on first order logic solvers. I think, yeah, there's some potential for that. I just don't think this should be the focus. This is just one space of solutions. We just need to imbue with more different kinds of abstraction spaces so that we have a higher chance of solving stuff. And yeah, that's my focus that I want to highlight. Of course, you can also learn this, but this takes a longer time to learn. So this can be done on the side. As you update your experiences, you can update your trajectories and learn the network here. But the more pertinent thing is how can we learn immediately from external memory?
Okay, I definitely get what you mean because in the paper it's really fascinating. What they really have is three abstraction spaces of memory. It's the persistent memory, which is kind of I think it's kind of like external, and you have your two your short-term memory and your long-term memory, which are like the two neural networks that were specifically training at train time to focus down tokens, memorize for test type, etc., all that. So what you really try to get at is that maybe that's not enough. Like the neurons are good, but we need more specialized kind of abstraction spaces, more abstraction spaces that will be have a higher hit chance for trajectories. The basically the Titans paper is good. It's a good direction, very in line with what you're trying to do, but it's not enough. It's still too vague, too on purpose, too human oriented, and we can really go a lot further with maximizing the symbolic side of things, maximizing the abstraction spaces, and have them be very specific and external as well, such as knowledge graph memories and kind of first order logic memories, etc., that are a lot more specialized and have a much better processing power behind it.
Definitely, yeah. So this is not a solved problem. There's a lot more work to be done in this, but the idea on multiple abstraction spaces, I'm very sure is correct. Okay, yeah, thanks for the question, Derek. Anyone else before we conclude for today? Maybe I take just one more if anyone wants to ask or some comments. Okay, if not, thanks for coming. I will just continue the rest of this next week because there's quite a lot of things new insights that I've gained so far. I want to also update my task gen stuff and the AGI stuff because there's new knowledge that I've learned. And yeah, so see you again next week for the continuation of this. Yeah, thanks so much.
Thank you.
Thank you.